So here to start Unit 2, we're going to talk about the historical development of atomic structure, because in class next time we want to talk about the way that we understand the atom is put together, but that picture of the atom, our current understanding of it, was a long process, and it's kind of important how we discover these pieces of the atom and where they go, and it'll kind of help you better understand some of the content that we're teaching you about those pieces. So our focus isn't going to be on dates, but I do kind of like to show you a timeline of these discoveries, because it's been a long road. The very first ideas of the atom were developed in ancient Greece with Democritus, all the way to our current understanding, current kind of picture of the atom that was in the 1930s. We really haven't had a whole lot of development in exactly what the atom looks like, or the pieces of the atom since then, at least on the whole atom scale. So it's been a long road, like I said. Also, like I said, our focus isn't on those dates. In fact, I'm not going to write down those dates again on any of these other slides. Our focus instead is on the people and their discoveries. So there's 4 main things you need to make sure to write down from each slide. Even though I'm probably going to have more information than you need on each slide, make sure that you have the name of the scientist that made that discovery, what they discovered, a summary of the experiment that they did. You do need to know what they did and kind of how that helped them make that discovery. And then, of course, what that brought to their idea of what the atom looked like. So their new picture of what they thought the atom was. On top of that, you may want to include a drawing with those words that you're using to describe what the atom looked like. I'll have a drawing of their idea of the atom on each slide, and a picture's worth 1,000 words. So, since you might see these pictures some other places, it might be a good idea to make a quick sketch, but at least get the words, descriptions down of what they looked like. So, first guy, that ancient Greek scientist, Democritus, which was back in 460 BC, was the first person that came up with the idea of the atom, and his word was atomos, which is Greek for uncuttable. So he was the guy that came up with the idea that somewhere there is an indivisible, smallest unit of matter that we now call the atom. Other Greek philosophers in the same day and age disagreed with him. They thought, well, no, you just can't cut that because you don't have a tool good enough to cut that. You could just keep cutting it and cutting it and cutting it, and the matter would just keep getting smaller and smaller and smaller, all the way down to an infinitely small piece. They thought that you could keep cutting and changing this matter into smaller and smaller pieces, no matter how far you went. And Democritus said, no, I think there's going to be a limit to that. I think we're going to get to a piece that is so small that you can't break it down, no matter how good or bad your technology is. And that's his idea of the atom. Now, as you might be able to tell, he didn't really do any true experiments. That's why I put scientist up there with ancient Greek in quotes, because really he was a philosopher. He was more talking about ideas and things, everyday examples that people could see and experiment with themselves, but it wasn't really true experiments. You could take a rock and break it and keep breaking it, and eventually you'd get to the smallest piece of that rock that you couldn't break anymore, a fleck of sand or dust, and he said that was a rock atom. You could do the same thing with cheese or water, get down to the smallest speck of any kind of matter, and he said that was an atom of that type. So his picture, his mental image of an atom was just a really tiny piece of that original substance that was solid, no empty space inside it, just that substance, super tiny, and homogeneous. It's all the same stuff that it was made of originally. It's just tiny, the tiniest piece of that matter. So I've drawn this little sketch over here, and I know that drawing spheres isn't always easy, but really what you need to focus on is getting a good circle to start with, and then we're going to draw an oval in the middle, starting with the solid section in the front. Draw kind of an arc there, and then you can kind of add a dashed section in the back, because you can't actually see that, but that adds some depth to our circle. So do the best that you can, but we just got a solid sphere here. The next guy on our list was John Dalton, and Dalton's atomic theory is an important part of atomic history, but he didn't actually have a new model of what the atom looked like. He didn't develop our understanding of what it looked like. He came up with rules that he realized all atoms have to follow that helped other people study the atom. So he didn't actually discover anything new about the atom. He just came up with these rules based on his reactions with gases on how these atoms are going to act and interact with each other. So that's our person, the experiment, and the model. And now we just need to fill in his rules. These are his discoveries here. All matter is composed of very small particles called atoms, so everything is made of atoms. All atoms of the same element are exactly the same. We could switch them out and they'd all look exactly the same. Atoms can't be created or destroyed. Back to that idea of atomos, they're uncuttable, undivisible, unbreakable. Atoms can combine in whole number ratios, so they combine with each other into new things, new substances, but they're always going to be whole atoms combining together. There's never going to be pieces of atoms combining. Back to that, we can't have them created or destroyed. They're always whole atoms. And in these chemical reactions where these substances turn into brand new substances, they're actually the same atoms. The atoms are moving around making a new compound or a new mixture, but they're not actually making new atoms. All of the atoms are exactly the same. So as you see, he had lots of rules for how atoms are going to act and interact, but nothing new about what the atom itself looked like. So this was in 1803. This is thousands of years since Democritus came up with his first idea of the atom. And yet, after Mr. Dalton came up with these ideas, we got to the level of technology where it took less than 100 years for Mr. Dalton to make his rules and then lead to the discovery of something new in the atom. So this electron that was discovered in 1897, so less than 100 years after Mr. Dalton came up with his rules. So this is where things start going faster and faster. And Thomson was the guy that discovered the electron, and he used that fancy setup that you see a sketch of there in your packet. It's called the cathode ray, and that's the same kind of thing that's at the back of any of those big, not flat screen TVs, the old TVs. They all had a cathode ray tube in the back that shot the light at the front of the screen to make the screen actually light up and show a picture. Well, Thomson was playing around with cathode ray tubes a little bit closer to when they were discovered, and they were all the rage. I mean, you could make this light from electricity, and you could make these glowing tubes of light. It was really cool, and he was one of the first people that realized that if you shot that cathode ray between magnets, then the beam always bent towards the positive plate, the positive side of that magnet, no matter where he put it. In this drawing, it's on the top, but he moved these plates all around, and no matter where he put it, top, bottom, left, right, the beam always bent towards the positive plate. And as we know now, and he knew then, opposite charges attract. So if this beam is made out of something that's bending towards the positive plate, the beam must be made out of something negative. So that was his experiment, is this cathode ray tube. And he basically discovered some little negative chunks in the atom. And that's all that he thought that this was. He called it the plum pudding model. We don't really have much plum pudding here in the United States, especially in this day and age. So maybe just think of a chocolate chip cookie, where the chocolate chips themselves are the electrons, and they're just scattered throughout the rest of the cookie dough itself. And that dough is positively charged. And he knew that because we knew the atom itself was neutral, which must mean that if there were negative charges, there was an equal amount of positive charges there to cancel it out. So as he discovered this negative thing, he knew there had to be some positive stuff there, but he just kind of figured, okay, the negative stuff is scattered in the atom and the rest of it is positive so that it all looks neutral. The next big discovery about the atom was the nucleus, and the guy that discovered the nucleus was actually Mr. Rutherford, and he was one of Thomson's students, grad students, worked in the lab and helped him with his discovery of the electron. But Rutherford really didn't agree with Thomson's image of the atom itself. He didn't think that plum pudding model was really sound, and so he spent a lot of time, about a decade or two, trying to come up with a different experiment, different results to prove his instructor, his teacher, wrong. And his experiment was called the gold foil experiment, where he took some radiation and shot it at gold foil. And this gold foil, it's important that it's foil because that means it's really, really super thin, like 1 or 2 atoms thick foil. And when shooting a positively charged particle, radiation, at it, you'd imagine that if we did have that plum pudding model where it's mostly this positive, mushy dough, surrounding these little negative electrons, that positive and positive would repel, and most of that stuff would bounce straight off if the plum pudding model was correct. But it didn't. Most of that beam, most of those positively charged radiation particles went straight through that gold foil, despite the fact that it was only an atom or two thick, and it should be hitting straight onto those atoms. So that must mean that there was nothing to hit in that atom. Most of the atom must be empty space. But, and this is important, there were some of those particles in that beam that did bounce off, either a little to the side or back at the radiation source. So there was actually something to the atom. It wasn't all empty space, but it was mostly empty space. So all of the mass, all of the matter in an atom must be really, really concentrated into a super tiny, small, dense positive charge in order to repel that positively charged radiation that was being shot at it. So this is what we call the nucleus model. He discovered the nucleus model. It's just the idea that most of the atom is empty space. Notice my little dashed lines around this picture here. And most of the atom is in that really tiny center nucleus. And technically that nucleus should be really much smaller if we were doing this to scale. But a tiny nucleus, everything in the atom is basically empty space except for that. We got some electrons scattered around, moving so fast, but those don't have enough mass for us to worry about when it came to reflecting that radiation. And then the final big discovery about the atom and its structure was how electrons are arranged, because even when Rutherford put them out into that big open space in his nucleus model, he didn't really know what was going on, and kind of like Thomson, he was like, oh, just scatter them around, have them moving, it's all random, right? Well, Mr. Bohr discovered that it wasn't all completely random, and we're actually going to recreate his experiment and do some examples with this, because there's a lot more to this experiment than what we're going to go into today. But let's actually focus on, well, how are the electrons arranged first? Bohr discovered that electrons are arranged in predictable orbits around the nucleus that we call energy levels. And he discovered this by burning stuff. His experiment was called the flame test. And he basically burned lots of different chemicals, compounds, elements, and looked at the pretty colors that they made. But more than just looking at the pretty colors, he measured the light. And every different color of light has its own energy. So there's lots of different greens in the electromagnetic spectrum, and each different green has its own specific energy. And what he noticed by making these measurements was that he only saw certain colors of light produced when he burned elements. Different elements tended to make different colors. Some of them might be the same, but each element kind of had its own fingerprint, its own set of colors and energies of light that it always made. And even when looking at different elements, there were some certain colors, some certain energies of light that he never saw. And at this point, they knew that this light that was being created came from electrons, much like those cathode ray tubes back in Mr. Thomson's day. So they knew that. And so he made the connection, well, if I'm only seeing certain energies of light, there must only be certain energies allowed for electrons in the atom, only certain energy levels that are allowed in our atom. And so that's where this planetary model came from. The idea that electrons are going to orbit the nucleus in energy levels kind of like the planets orbiting the sun, but in 3 dimensions, not all in a flat sphere, but kind of turning each of these in its own kind of direction, but still in a much more organized fashion than what Thomson or Rutherford would have predicted. So we use the Bohr model a lot. It's a really pretty good model that we know isn't 100% true, and we'll talk about modern atomic theory here in just a moment, but it's pretty good, and it's good enough for basic chemistry these days. So this was around 1913, so it's at least, well, it's actually not this century, but it's closer to 100 years from now instead of, like hundreds and thousands of years before. So let's get to our modern idea of the atom. Modern atomic theory, we're actually going to kind of compare and contrast to Dalton's atomic theory, but I do want to remind you, or start with the model. Nowadays, we know Bohr isn't quite right. We currently accept what's called the electron cloud model. And if you're making these drawings, do your best with this one. But the general idea of this electron cloud model is that we have all different kinds of shaped orbitals and energy levels that our atoms can be on. Some of them are spherical, like Bohr thought. Some of them are these weird little peanut shaped, and it all kind of ends up combining together to look a little bit like a cloud. If you can kind of visualize this, like a little simple cloud that like a kindergartner would draw, and I'm totally rocking it. And while we are going to fill in this 1, 2, 3s with the current ideas, the current rules that are true, notice there's only 3 things that we currently accept as true in this modern atomic theory, where Dalton had 5. So 2 of his rules are actually not true anymore. And I actually want to talk about the things that aren't true and why very briefly before we fill in our 1, 2, 3s here. So the 2 rules that aren't true, technically, are 2 and 3. All atoms of the same element aren't exactly the same. We're going to talk about things called ions and isotopes in class next time, and those are how we can have the exact same element of carbon, but have a couple different variations of carbon. And then in 3, Dalton said atoms can't be created or destroyed, but that's actually false. Even though it's not matter anymore after we destroy it and break it down farther, we can actually break down atoms and turn them into different atoms even. So nuclear chemistry, nuclear reactions, which is actually how we're going to finish out this unit, is a way that Dalton was proved false. So let's get these 3 ideas down that were true. So all matter is composed of atoms. Atoms do combine in whole number ratios, and in reactions, atoms do only rearrange. So make sure you got these 3 things here and that electron cloud model, and maybe your best guess at drawing that picture. And that's it.